Hi, welcome to a series of videos I'm making as helper videos for the exponential functions test for those of you who might need to do a do-over on it. I've created problems that are similar to the ones that were on the test, and I'm going to go ahead and work through some of them with you. So here we have a situation which is fairly similar to the problem involving the pickle bears on the original test. We have kudzu, which is an invasive species of plant life that can overtake a community in a matter of weeks. If it is spreading at a weekly rate of 53% and starts by covering 25 square meters of area, that's a 5 by 5 meter area in Mississippi, about the size of a classroom at our school. How long will it take to cover all of Mississippi, which is about 125,430,000,000 square meters? Okay, so first we're going to do this as a weekly growth rate with just weekly compounding. And then we'll have to figure out the same weekly growth, only compounding daily. And then finally, we'll figure it out compounding continuously. Let's start off with the information we have. We know that we have a starting amount. That's one thing we need. We also know we have a weekly rate of 53%. So that tells us something about how it's expanding. Now we know it's a growth rate, so our growth rate can't be just 0.53 because that would be decay. We know it's exponentially growing. Actually, I didn't state that in the problem, but things that are living biological systems tend to grow at in an exponential way. So let's start off, though, by setting up the parts of the function. We know our exponential function is going to be y equals, basic one is ab to the x power, where a is our initial value, b is the base, the growth or decay rate, and x is the number of rounds of growth or decay that have happened. That's the number of times we're using b as a factor. Okay, we can do various things with it. We're going to, in this case, we're going to be dealing with a compounding situation. So instead of doing it like this, we're going to write our initial value will be called P, is the structure. We're going to say 1 plus a rate over a number of compounding events. Okay, and that's going to be raised to the number of compounding events times time. Okay, so that's the basic structure. So we need to figure out what is our P. P is going to be 25 because that's our initial value. All we're doing right now is setting up a basic equation. Later on, we got to deal with this question of 125.43 billion. Okay, so our rate is 0.53. So we say 0.53. And then we have different versions for the number. I'm going to leave that alone for right now. I'm going to get rid of the word time, since time is going to be just x, okay, on our graph. Okay, so that's going to be the basic function that we'll use for A and B. For A, let me just back up and lay out a couple things about this. For A, do this here. A, the number of compounding events is just 1 in a week. So it's a weekly rate. So our weekly rate is 1 plus 0.53. So overall it's a 1.53 rate. Our number of compounding events is 1. And so then that number is used as a denominator for splitting up the 0.53 one way. So we don't really care about it. So we can actually make that go away. It's just that. We don't really care about the fact that there's a 1 times the number of weeks. We're basically saying x is weeks here, so that's just x. Okay, so we've got that equation, and what we need to do is we need to see when that equation intersects with 125.43 billion. So I need to make a second equation that's 125 and then 430, 0, 0, 0, 0, 0, 0. That is, I'll put commas in here. When I'm in Desmos, I'm not going to use commas. Okay, so that's when y equals that amount, that's what we're trying to figure out is when this function equals that amount. So if we graph this function on Desmos and we find the intersection with this value, then we will actually have an x value that's associated with that intersection. And that x value will be the number of weeks. So let's go ahead and go into Desmos. So Desmos, we're going to do this function. Desmos is going to object probably at first, so I'm going to do it that way. So 25, and that x needs to be in an exponent position. I got to do that again. Okay, so there's my basic function. And then we need to have a second function at y equals 125 for 430 million. Million is going to be 6 more zeros. Let me make sure I've got that. 1, 2, 3. 1, 2, 3, 1, 2, 3. So I've got 125 followed by 9 place values. And I think we're good. Okay, at this point you were like, okay, that's going to be a lot of zooming out. I could do that. I could just go zoom, 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 zoom. Oh, that's going to take forever. So instead, I'm going to use my handy dandy setup tool here, and I'm going to go to x-axis. I'm actually fine with x-axis being something like -5 to, we'll make it 40. My y-axis, though, I really want my y-axis to be something a little more useful. I'll say -4 to 126 billion. And that should do it. Let's see what happens. Oops, I did the wrong one. So let's go back. Look at that. I think I did it. No, maybe. I need to start over. Okay, so my x-axis, it looks like I did it to my x-axis instead of my y-axis. So we're going to try that again. I'm going to go back. So sometimes we'll goof up. So I'm going to go back to my default zoom. I'm going to go here. I'm going to change I'll change my x-axis to -5 to 40. I'm going to change my y-axis. I'll leave it at -6 point blah, blah, blah. I'm going to change it to 126. I'm going to put 9 zeros to make it 126 billion. Okay, I've done that, and clearly I am beyond, and my intersection point is beyond there, so I'm going to have to change my x-axis again. So I'll change my x-axis. We'll make that 400, and now my intersection is on the screen. Okay, so now I know how many weeks it will take. So this here is my y value. That's the 125,430,000,000. It sets it up in scientific notation format, as you can see. But that's what that is. And then over here is my x value. My x value is 52.523. Now that's weeks, and there are 52 weeks in a year approximately. So that means it takes about a year for the kudzu to take over all of Mississippi, assuming Mississippi were a perfectly round thing, which it's not. But it would cover the area equivalent to Mississippi in about 52 weeks, 52 and a half weeks. So then we go back to our original thing, and we can say, okay, it will take about 52.5 weeks, or about a year, to take over an area as big as Mississippi. Okay, I'm going to now pause and pick up on the next ones in a second.